ఈ రోజు మనం మ్యాగ్నెటిక్ మెటీరియల్స్ గురించి డిస్కస్ చేయబోతున్నాం. ఇది మనకి R25 సిలబస్ లో 4th యూనిట్ లో ఒక పార్ట్ మ్యాగ్నెటిక్ మెటీరియల్, అదర్ పార్ట్ వచ్చేసి డైఎలక్ట్రిక్. సో ఈ మ్యాగ్నెటిక్ మెటీరియల్స్ లో మనం డిస్కస్ చేయబోయేది ఏంటంటే మ్యాగ్నెటిక్ మెటీరియల్స్ అంటే ఏంటి, మనకు తెలిసిన మ్యాగ్నెట్స్. అయితే ఈ మ్యాగ్నెటిక్ మెటీరియల్స్ గురించి మాట్లాడాలి అంటే మనకు కొన్ని బేసిక్ టెర్మినాలజీ తెలిసి ఉండాలి. ఆ డెఫినేషన్స్, బేసిక్ టెర్మినాలజీని డిస్కస్ చేస్తాం. తర్వాత జనరల్ గా మ్యాగ్నెట్స్ కి మ్యాగ్నెటిజం అనేది ఎలా వస్తుంది, ఈ మ్యాగ్నెటిక్ మూమెంట్ ఏంటి, అది ఎలా వస్తుంది అనేది ఈ ఆరిజిన్ ఆఫ్ మ్యాగ్నెటిక్ మూమెంట్ లో డిస్కస్ చేస్తాం. ఈ మ్యాగ్నెటిక్ మూమెంట్ అనేది కీ రోల్ ప్లే చేస్తుంది మ్యాగ్నెటిజం మొత్తం. తర్వాత బేస్డ్ ఆన్ నేచర్ మ్యాగ్నెటిక్ మెటీరియల్స్ ని డిఫరెంట్ టైప్స్ లో క్లాసిఫై చేసాం. పారా, ఫెర్రో, యాంటీ మ్యాగ్నెటిక్ మెటీరియల్. సో ఈ డిఫరెంట్ మ్యాగ్నెటిక్ మెటీరియల్స్ క్లాసిఫికేషన్, అవి ఎలా అరైజ్ అవుతాయి, ఎలా ఐడెంటిఫై చేయొచ్చు, వాటి స్పెషల్ ప్రాపర్టీస్ ఏంటి, వాటిని ఎక్కడ అప్లై చేస్తాం, ఫైనల్ గా వాటి డిఫరెన్సెస్. ఇది వన్ ఆఫ్ ద ఇంపార్టెంట్ క్వశ్చన్. తర్వాత ఫెర్రోమాగ్నెటిజం లో వీస్ డొమైన్ థియరీ, అంటే డొమైన్ కాన్సెప్ట్ తీసుకొని వీస్ ఫెర్రోమాగ్నెటిక్ మెటీరియల్స్ లో ఆ మ్యాగ్నెటిజం కాన్సెప్ట్ అనేది ఎలా వస్తుంది అనేది ఎక్స్ప్లెయిన్ చేశాడు. దాన్ని డిస్కస్ చేస్తాం. తర్వాత హిస్టెరిసిస్ లూప్, అదే నథింగ్ బట్ BH కర్వ్. సో ఈ BH కర్వ్ నుంచి మనకేం తెలుస్తుంది అంటే రెమనెంట్ పోలరైజేషన్, కోయర్సివ్ ఫీల్డ్ ఎలా ఉంది ఏంటి అనేది తెలుస్తుంది మెటీరియల్ కి. దాంతో పాటు ఈ లాసెస్, అలాగే ఈ ఏరియా ఆఫ్ BH కర్వ్ ని బేస్ చేసుకొని మెటీరియల్స్ ని అగైన్ 2 టైప్స్ గా క్లాసిఫై చేశారు. సాఫ్ట్ మ్యాగ్నెటిక్ మెటీరియల్స్, హార్డ్ మ్యాగ్నెటిక్ మెటీరియల్. సో వాటిని ఎలా మ్యాగ్నెటైజ్, డిమాగ్నెటైజ్ చేయొచ్చు, అలాగే సాఫ్ట్ ఎలా ఐడెంటిఫై చేస్తాము, హార్డ్ మ్యాగ్నెటిక్ మెటీరియల్ ఎలా ఐడెంటిఫై చేస్తాం. తర్వాత సాఫ్ట్ మ్యాగ్నెటిక్ మెటీరియల్స్ అప్లికేషన్స్ ఏంటి, హార్డ్ మ్యాగ్నెటిక్ మెటీరియల్స్ అప్లికేషన్స్ ఏంటో చూద్దాం. దాంతో పాటు ఫైనల్ గా అప్లికేషన్స్ ఆఫ్ మ్యాగ్నెటిక్ మెటీరియల్స్ యొక్క అప్లికేషన్స్ చూద్దాం. గుడ్ ఈవినింగ్ ఇంజనీర్స్. ఇప్పుడు మనం మ్యాగ్నెటిక్ మెటీరియల్స్ లోని బేసిక్ పాయింట్స్ చూడబోదు. జనరల్ గా మ్యాగ్నెట్ అంటే ఏంటి, మ్యాగ్నెట్ అంటే ఇట్స్ ఎ మెటీరియల్ విచ్ అట్రాక్ట్ ద ఐరన్ అండ్ ఇట్స్ రిలేటెడ్ థింగ్, నికెల్, కోబాల్ట్, ఇలా మ్యాగ్నెటిక్ మెటీరియల్స్ ని అట్రాక్ట్ చేసేదాన్ని మనం మ్యాగ్నెట్ అంటారు. మ్యాగ్నెట్స్ అనేవి డిఫరెంట్ టైప్స్ ఉంటాయి, మనకు తెలిసిందే. బార్ మ్యాగ్నెట్, హార్ష్ మ్యాగ్నెట్, రైట్. సో మ్యాగ్నెట్ ఉంటే దానికి బేసికల్ గా 2 పోల్స్ ఉంటాయి, నార్త్ పోల్, సౌత్ పోల్. ఇక్కడ చూపించినట్టు ఈ మ్యాగ్నెటిక్ లైన్స్ అనేవి ఎప్పుడు కూడా అవుట్ సైడ్ ఏమో నార్త్ టు సౌత్ ఉంటాయి, ఇన్సైడ్ ద మ్యాగ్నెట్ వచ్చేసి సౌత్ టు నార్త్. కంపేర్డ్ టు ఎలక్ట్రిక్ లైన్ ఫీల్డ్స్ అనేవి ఓపెన్ లైన్స్, ఇవి క్లోజ్డ్ లూప్స్. మ్యాగ్నెటిక్ లూప్స్ అనేవి క్లోజ్డ్ లూప్. సో జనరల్ గా ఎలా చూపిస్తామంటే అవుట్ సైడ్ నార్త్ దగ్గర స్టార్ట్ అవుతుంది, సౌత్ దగ్గర టెర్మినేట్ అవుతుంది అని. యాక్చువల్ గా ఈ మ్యాగ్నెటిక్ లైన్స్ అనేవి క్లోజ్డ్ లూప్స్ లాగా ఫామ్ అవుతాయి, రైట్. ఇది మనకు తెలిసిన విషయం. సో ఈ మ్యాగ్నెటిజం గురించి డిస్కస్ చేయబోయే ముందు బేసిక్ డెఫినేషన్స్ అనేవి చూద్దాం. ఇంతకీ ఈ మ్యాగ్నెటిజాన్ని ఎలా డిఫైన్ చేస్తామంటే ఇట్స్ అట్రాక్టింగ్ ప్రాపర్టీ ఎగ్జిబిటెడ్ బై ఎ మ్యాగ్నెట్. సో వేరే వాటిని అట్రాక్ట్ చేసే ప్రాపర్టీ చూపించేదాన్నే మ్యాగ్నెట్ అంటాం, ఆ ప్రాపర్టీనే మ్యాగ్నెటిజం అంటాం. సో బేసికల్ గా మ్యాగ్నెటిక్ డైపోల్ అంటే ఏంటంటే ఎనీ 2 ఆపోజిట్ పోల్స్ సపరేటెడ్ బై ఏ డిస్టెన్స్ కాన్స్టిట్యూట్ ఏ మ్యాగ్నెటిక్ డైపోల్. సో ఒక చోట సౌత్ పోల్, ఇంకొక చోట నార్త్ పోల్ ఉందనుకోండి, ఈ రెండింటి మధ్య సమ్ డిస్టెన్స్ ఉంటే దీన్ని మ్యాగ్నెటిక్ డైపోల్ అంట. సమ్ డిస్టెన్స్, 2 opposite poles separated by a distance constitute a magnetic dipole. So ఇది magnetic dipole. Then what is magnetic movement? So magnetic movement ni ఎలా define చేస్తాం? So magnetic movement is defined as the product of the pole strength and distance between the 2 poles of the magnet. Suppose మనం ఒక బార్ మ్యాగ్నెట్ తీసుకున్నాం. ఈ బార్ మ్యాగ్నెట్ ఇటు నార్త్, ఇటు సౌత్ ఉంటే దీని డిస్టెన్స్ వచ్చేసి 2L మొత్తం లెంత్. దాంతో పాటు ఈ పోల్ స్ట్రెంగ్త్ M అయితే ఈ మ్యాగ్నెటిక్ మూమెంట్ ని ఎలా డిఫైన్ చేస్తామంటే 2L into M. యూనిట్ వచ్చేసి ఆంపియర్ స్క్వేర్ మీటర్. దిస్ ఈస్ అబౌట్ మ్యాగ్నెటిక్ మూమెంట్. నెక్స్ట్ మ్యాగ్నెటిక్ ఫ్లక్స్ డెన్సిటీ ఆర్ మ్యాగ్నెటిక్ ఇండక్షన్. ఇది వన్ ఆఫ్ ద ఇంపార్టెంట్ డెఫినేషన్. సో బేసికల్ గా మ్యాగ్నెటిక్ ఫ్లక్స్ డెన్సిటీ ఆర్ మ్యాగ్నెటిక్ ఇండక్షన్, దిస్ ఈస్ డిఫైన్డ్ యాజ్ ద నంబర్ ఆఫ్ మ్యాగ్నెటిక్ లైన్స్ ఆఫ్ ఫోర్స్ పాసింగ్ పర్పెండిక్యులర్లీ త్రూ యూనిట్ ఏరియా. సో ఇవి మ్యాగ్నెటిక్ లైన్స్, ఇవి పర్పెండిక్యులర్ గా ఈ సర్ఫేస్ కి పాస్ అవుతూ ఉంటే ఈ number of lines per unit area that will give magnetic induction or magnetic flux density Weber per square meter or Tesla is the unit. So if it is the circle, area of the circle will be pi r square, and if we are taking a rectangular sheet, area of the rectangle is length into breadth. So like that we will use number of the lines per unit area that will give magnetic induction or magnetic flux density. Then magnetic field intensity. The magnetic field intensity at any point in a magnetic field is force experienced by a unit north pole placed at that point. So magnetic field లో గనక ఒక another magnet ని తీసుకొస్తే ఆ యూనిట్ నార్త్ పోల్ అనేది ఎంత ఫోర్స్ ని ఎక్స్పీరియన్స్ చేస్తుందో దాన్ని మ్యాగ్నెటిక్ ఫీల్డ్ ఇంటెన్సిటీ అంటాం. సో యూనిట్ వచ్చేసి ఆంపియర్ పర్ మీటర్. సింబల్ హెచ్ వాడతాం, ఇది బి వాడతాం. సో ఈ రెండింటికి మ్యాగ్నెటిక్ ఫీల్డ్ ఇంటెన్సిటీకి మ్యాగ్నెటిక్ ఫ్లక్స్ డెన్సిటీకి కనెక్షన్ రిలేషన్ ఇస్ దేర్. సో మ్యాగ్నెటిక్ ఇండక్షన్ డ్యూ టు మ్యాగ్నెటిక్ ఫీల్డ్ ఇంటెన్సిటీ అప్లైస్ ఇన్ వాక్యూమ్ రిలేటెడ్ బై B is equal to mu naught H. So if we want to calculate mu naught, we can write B by H, where mu naught is a permeability of free space, that is given by mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. So if the field is applied in a medium, so if we are taking this concept in the medium rather than in vacuum, then B is equal to mu H, where mu is permeability of the material in the medium. So magnetic field intensity is also defined as the ratio between magnetic induction and permeability of the medium. H is equal to B by mu. This relation we will use number of times. Then magnetic permeability, the ratio of the magnetic induction to the applied magnetic field. Just know whatever we defined, that's the same thing. Henry per meter is the unit. Next one is relative permeability. So it is defined as permeability of the medium to the permeability of the free space. Mu r is equal to mu by mu naught. That is a relative permeability. This is the ratio, so no unit. If it is the ratio of same term, it's a no unit. Then intensity of magnetization, I or M we use. The magnetic moment per unit volume. So I is equal to capital N U, where N is number of atoms per unit volume and mu as the average dipole moment. Next terms is important one, magnetic susceptibility. It's the ratio of the intensity of magnetization to magnetic field intensity. Psi is equal to I by H. It has no unit. That may be positive or negative. Then relation between B, H and I. B is equal to mu H. Mu can be written as mu naught into mu R. Then we can add and subtract mu naught H. Then we manipulate these terms in such a way that finally we will get the relation B is equal to mu naught into H plus I. So in these three terms, four terms, if we know the three terms, anyhow mu naught is a constant one. So in out of three, if we know the two, the third one easily we can calculate. So this will be very useful in problem solving, right? Thank you. Hi engineers, now we are going to discuss about origin of magnetic moment. So basically magnetic properties of the solid arises due to the electron's motion in the atom. So whenever electron is moving in the atom, this gives rise to magnetic nature or magnetic moment. So on that line we are going to discuss this one. So in atoms, permanent magnetic moment arises due to the following. One is orbital magnetic moment of the electron, spin magnetic moment of the electron, final one spin magnetic moment of the nucleus or nuclear spin. So orbital magnetic moment, then spin magnetic moment of electron as well as nuclear spin. These are the three concepts which contribute for the origin of magnetic movement. So total magnetic movement is always sum of these. As picture shows, this total magnetic movement is equal to orbital of electron orbiting nucleus, this will, and spin magnetic moment, that may be opposite. So if we subtract that, what will give total magnetic moment, right? We will see one by one. So orbital magnetic moment. So as shown in the figure, whenever electron revolving in the orbit, it gives rise to, whenever charge is moving, it gives rise to the current or charge. The flow of the charges gives rise to the magnetic field. That's the whole story. So orbital magnetic moment, how we will calculate? Already we know whenever electron is moving, it generates the current. So I is equal to Q by T. Here we are using small amount. That's why I is equal to dq by dt. When we multiply it with this ds is nothing but this circumference of the s is the circumference of the orbit. Small portion we are considering. That's why it's a ds. When we multiply with the ds and we reshuffle it, we shift it to here this one and here this one. ds by dt, it will become velocity and we will get dq separate. Ids is equal to dq into v. So angular velocity we already know. Omega equal to v by r. V is equal to r omega. And circumference of the orbit. This is a circular shape. Circle circumference is 2 pi r. Now the idea is very simple. By using equation 1, 2, 3, we have to manipulate the term. So if we substitute and equate, finally what we have to get? We have to get the current. Once we got the current expression, magnetic moment produced by the dipole, we have to calculate. That is mu m is equal to current into area. This is the circle. So pi r square is the area of the circle. So on simplification, we will get mu m is equal to minus em omega r square by 2m. In that we will substitute orbital angular momentum L is equal to m omega r square. This is the standard expressions. Those things we will substitute. So orbital angular momentum of the electron is the L. So the possible orientations of vector L, ml into h cut. H cut stands for h upon 2 pi, right? ml into h by 2 pi. ml is a magnetic quantum number, h is a Planck's constant, 2 pi is a constant value. So by using this, we can write and simplify the expression, and finally we will extract Bohr magnetron. That is EH by 4 pi m is called the Bohr magnetron. Mu m is equal to Bohr magnetron into ml, right? That is the first one, mu m we get. Then spin magnetic moment of the electron. Spin magnetic moment of the electron, mu s is equal to minus e by 2m into s. Spin angular momentum, S is equal to ms into h cut. So these are standard expression in quantum physics or quantum mechanics. From there we will take orbital angular momentum and spin angular momentum expression. So ms into h by 2 pi. Then spin quantum number. Then substituting in equations, finally we will get spin magnetic momentum as plus or minus mu b by 2. What is this mu b? Mu b already we calculated, that is nothing but our Bohr magnetron. So Bohr magnetron, mu s is equal to plus or minus mu b by 2. Then spin magnetic moment of the nuclear. So nuclear spin magnetic moment. Nuclear spin is given by mu n is equal to eh by 4 pi mp. mp stands for mass of the proton. That is the standard value. Here we are taking. Substituting all the values, we get m, nuclear spin is equal to 5.05 into 10 power minus 27 ampere square. So if we want to get a total magnetic moment, we have to add these three: orbital angular momentum, then electron spin, nuclear spin. If three parameters we will add, we will get total magnetic moment. Then what is the significance of this magnetic moment? Why we want to know about? So the magnetic moments decide how material behave, like whether it acts as a diamagnetic or paramagnetic or ferromagnetic. This magnetic moment will decide. Then in MRI, magnetic resonance in MRI, magnetic resonance imaging, hydrogen atoms magnetic moments help create clear images of human body. In MRI scannings, we use this concept. Then spintronics uses electron magnetic moments to make faster and smarter electronic devices. Spintronics means spin-based electronics. Spin-based electronics, what we call spintronics. Then in quantum physics, magnetic moments help us understand atoms and how tiny particles be. So there is a significant role they will play in different concepts, right? Thank you for listening this part. Hi engineers, in this section we are going to discuss about the classification of magnetic materials. So when come to the solid, they are mainly classified into two types magnetic material. One type of materials has atoms having a no permanent dipole. So this is the classification based on whatever we discussed now, that is magnetic dipole moment based. So atoms having no permanent dipole moment, those are come under diamagnetic material. And when come to other section, atoms having permanent dipole moment, these are paramagnetic material, ferromagnetic material, anti-ferromagnetic material, and ferrimagnetic material. So this is the classification. Now we will move further and classify these magnetic material. Basically what we told, one type of material, diamagnetic materials, there is no magnetic dipole moment generally present there, right? For other dipole moments exist, and based on the orientation of the spins of the dipoles, in paramagnetic orientation will be this, and ferromagnetic all are oriented in the same direction. In anti-ferromagnetic, they are pairs, some are upwards, some are downwards, means opposite direction orientation. Then ferrimagnetic material, there is, if we carefully observe, there is a difference. The dipole, some are small, some are large, maybe one side large, another side small. Orientation is opposite tone, but when come to ferromagnetic, they are same direction. So yeah, before going to further, we will broadly classify as diamagnetic, paramagnetic, ferro, antiferro, ferrimagnetic material. Now we will see one by one. So when diamagnetic materials which become weakly magnetized in the direction opposite to the applied field. So generally, if no field is applied, there is no magnetism, because these are the diamagnetic materials. And generally diamagnetic materials, all electrons are paired, right? All electrons are paired. In those materials, diamagnetism exists. So in the universe, every material is a diamagnet, but due to special properties, other para, ferro, antiferro properties will dominate. So as a default, all materials are diamagnetic materials. And when come to this magnetic movement, generally they won't exist, or if we apply magnetic field, they may be slowly arise, weakly magnetized, and that too, whenever we apply the magnetic field, these magnetic moments aligned opposite to the direction. That type of materials what we call diamagnetic material. So when come to diamagnetic material, the properties are very straightforward. Its relative permeability is less than 1, and magnetic susceptibility is negative, and psi is independent of temperature and magnetic field strength. Net magnetic moment is 0. That's why there is no magnet, and no permanent dipole. No permanent dipoles exist in diamagnetic material, and diamagnetic materials repel magnetic lines of force. So whenever we keep a diamagnetism in a magnetic field, it repel the line, like magnetic lines are there. If it is magnet, then we will see. And most our superconductors are diamagnetic, that's why they will show the Meissner effect. And examples are organic materials, bismuth, zinc, copper, silver, gold, etc. So all these materials are diamagnetic material. Next comes the paramagnetic materials which become weakly magnetized in the direction of applied magnetic field. So without application of the field, the dipoles exist, but they are randomly oriented. Magnetic movements different directions. So whenever we apply the magnetic field, they oriented in the direction of applied field, along the direction of applied. Those materials are called paramagnetic materials. Now when come to the properties, its relative permeability is greater than 1 but very small, and magnetic susceptibility is a low and positive. When come to dia, it's a negative. Then psi is independent of applied magnetic field H, but depends on T. That gives Curie-Weiss law. Psi is equal to C by T minus theta. Then net magnetic moment μm not equal to 0. So μm is not equal to 0. Permanent dipoles are present. In diamagnet, no permanent dipoles, but here permanent dipoles exist. Paramagnetic materials weakly attract the magnetic lines of the force. So whenever we keep the paramagnetic materials in magnetic field, they weakly attract the magnetic line. Spin alignment is random. Example for this: sodium, aluminium, manganese, phosphorus, etc. Then ferromagnetic materials. So materials acquires high magnetization in a weak magnetic field also. The main reason for this is they have the oriented dipole. And when come to the properties of ferromagnetic materials, relative permeability is very high compared to 1. Magnetic susceptibility is large and positive. Magnetic susceptibility, net magnetic moment, mu m not equal to 0. These magnetic materials possess permanent dipoles are present, so they will possess permanent dipole. Ferromagnetic materials attract the magnetic lines of force strong. So when come to paramagnetic, they weakly attract. When come to dia, they will repel. Spin alignment is parallel and is in the same direction. These materials exhibit hysteresis. These materials consist of domains. So based on the Weiss domain theory, we will explain these ferromagnetic properties. Example: ferrous, cobalt, nickel, gadolinium, etc. Then comes anti-ferromagnetic material, materials in which spin alignment is anti-parallel and net magnetic moment is, so spins of neighboring atoms are aligned anti-parallel. So these spins are anti-parallel. Magnetic susceptibility is a small and positive. Magnetic susceptibility greatly depends on the temperature, right, as shown in the diagram. Then net magnetic moment equal to 0. So this net magnetic moment is 0. And the Néel temperature we can see. Below the Néel temperature, this magnetic susceptibility is slowly increasing. Néel temperature, it's maximum. As I go on temperature, its psi value go on decreasing and finally became 0. Then these are Fe2O3, manganese oxide, chromium oxide. These type of the material shows anti-ferromagnetic nature. And ferrimagnetic materials, materials in which anti-parallel spins of different magnitudes and large magnetization arises. So ferrimagnetic material in which anti-parallel spins of different magnitudes and large magnetization arises. Here this one, opposite spins but different anti-parallel spins of neighboring atoms are aligned anti-parallel of different magnitudes are different. Magnetic susceptibility is very large and positive, right? This is ferri, other side it is para. Magnetic susceptibility greatly depends on the temperature. Net magnetic moment not equal to 0. Above Curie temperature, material behaves as paramagnetic, while below the temperature it behaves as a ferrimagnetic material. This is the critical temperature. Examples of ferrous, ferrite, nickel, ferrite, etc. Then these are the overall idea how the temperatures versus magnetic susceptibility graphs will be, and the alignments of the spins as well. Now comes in exam, sometimes they will ask compare the types of magnetic materials. In that scenarios, we have to make a table like diamagnetic material, para, ferro, antiferro, and ferrimagnetic material. Then we have to compare each step. Net magnetic moment exists in the presence of magnetic field in opposite direction. Net magnetic moment exists in the direction of applied field. In the direction of applied magnetic field, this is opposite direction. Large net magnetic moment exists in the direction of applied field, in the same direction, and in the direction exists in the direction. So when come to diamagnetic, it's opposite the direction, remaining all in the same direction. But ferromagnetic material, it's a large net magnetic moment. There is an induced magnetism opposite to the applied field. There is an induced magnetism in the direction of applied. So in the direction, once the first point is in the direction, second one is also on the same line. Third one, it repels the magnetic lines of force due to external magnetic field. So diamagnetic repels, it allows pass through it. It allows large number. Limited number it will allow, but when come to ferro, it large number. It allows magnetic lines of force to pass through it. It allows large number of lines of force pass through it. Next set, relative permeability. It's a negative value, less than 1, and it's a greater than 1, much greater than 1, greater than 1, much greater than 1. Then since the induced magnetic moment is opposite to the direction of the applied field, the intensity of magnetization is negative. M is negative. Here M is positive and moderate. Then here M is positive and high. M is positive and moderate. M is positive and high. Right. So whenever you are writing, you take care of the key points, you can write the remaining thing. Susceptibility is negative, low and positive, high and positive, low and positive. It's a high and positive. Then susceptibility and temperature relation. It's a plays the key role. It's a susceptibility size independent of the temperature. In all other cases, it's depend, and the relation is, this is the Curie's law, this is Curie-Weiss law. This is also same relations it will. When come to examples, alkaline metals and transition metals, it's a transition and rare earth metals, salts of transition elements, and ferrite. So these are the different combinations, right? Okay, thank you. In this lecture, we are going to discuss about the Weiss field theory of ferromagnetism. So in 1907, P. Weiss proposed a molecular field theory to explain qualitatively the nature of ferromagnetism, how the magnetic materials getting this ferromagnetism. Then Weiss postulated that an internal molecular field causes the parallel alignment of the dipole and set up spontaneous magnetization in ferromagnetic materials. This is the overall idea. So in order to justify that idea, he proposed or hypothesized the concept of domains. What is domain? Domain is a small region. Like what he did is, he assumed that solid or maybe any ferromagnetic material consists of a small parts of the region. Each region he treated as a domain, and in the domain the net or all the in the domain the net polarization is in the same direction. So each domain has a different net orientations without field applications. When we apply the field, they will oriented into the same direction. That gives rise to magnetization. So in each domain, spontaneous magnetization is due to parallel alignment of all magnetic dipoles. So in a single domain, all dipoles oriented in same direction. That's the assumption. The direction of spontaneous magnetization varies from domain to domain. So here we can see spontaneous magnetization, this is oriented in different domains in different directions. So that leads to overall net magnetism is almost negligible or equal to 0. So that is the reason. Without a field, it will be 0. But when we apply the external field, there happens two things. For the alignment of the randomized domains, already randomized, they will align into the same direction. One is by motion of a domain walls, another one rotation of the domain. So what happens is, the volume of the domains that are favorably oriented with respect to the magnetized field increases. Then rotation of the domain. When the applied magnetic field is strong, rotation of the direction of magnetization occurs in the direction of the field. Rotation will take place when we apply the strong field. If field is strong, then only rotation will take place. Otherwise, even though with a small field also, the motion of the domains will take place. That thing we can see here. Whenever we initially consider, these domains are randomly oriented. So whenever we apply the field one particular direction, so if we are applying the field in this direction, what happens? Whatever the domains are there in the directions, they start increasing, and other direction domains start decrease. But if we increase the field, once the field is got increased, then we will get rotation of the domains also. This will play key role in the explanation of hysteresis effect. So this is a B versus M curve. Up to some particular point, growth of the favorable domains will take place and unfavorable domains will get shrinkage. Then if we go to higher fields, then automatically rotation of the domains will take place. These are the two factors that will decide, right? Thank you. హాయ్ ఇంజనీర్స్, ఈ లెక్చర్ లో మనం హిస్టెరిసిస్ కర్వ్ గురించి తెలుసుకోబోతాం. ఏంటి హిస్టెరిసిస్ కర్వ్, దీనివల్ల యూస్ ఏంటి మనకి అంటే ఈ మ్యాగ్నెటిక్ మెటీరియల్స్ యొక్క నేచర్ అర్థం చేసుకోవడానికి, దాంతో పాటు అప్లికేషన్ పాయింట్ ఆఫ్ వ్యూ లో కూడా ఈ హిస్టెరిసిస్ కర్వ్ అనేది చాలా యూజ్ అవుతుంది. ఏంటి ఇంతకీ హిస్టెరిసిస్ ఏంటంటే ద ferromagnetic material refers to the lagging of a magnetization behind the magnetization field. So BH, or I also we can consider. So in this curve, what we will do is we will try to understand what we will do and how this curve will be formed. So whenever we are drawing the curve, initially we will be at O center. Whenever we are go on increasing a magnetizing field, then the curve automatically moves to this line. And whenever we decrease the magnetizing field, means moving in reverse direction, slowly it will decrease and moves. Even though we will bring magnetizing field to 0, some portion of the B value remains there. That is what we call retentivity. Then in order to make that retentivity 0, we will apply further magnetizing field in opposite direction and finally make that B or I value as a 0, and the magnetizing field for that purpose whatever we use, that is what we call coercivity, and we will move opposite direction. Slowly it will decreases and finally it will get saturation in opposite direction. And when we increases again, it won't go in the same direction. It will take the different path. In this path, it will move from B to E and E to F and F to A. So even though we will decrease and increase in cycles, it won't take the same path. Like a loop, it will form. This loop, what we call hysteresis curve, and the region between these or the area of the loop will give a lot of information about the nature of material as well as the losses present inside. Now we will, whenever magnetic material is placed in external magnetic field, magnetization increases and reaches maximum point called magnetic saturation. Then if the magnetic field is reduced, once we reduce, as we told previously, it will take the path from A to B to C to D, finally negative direction. If we are decreasing, magnetization decreases but follows a different path instead of the original one. Even when H becomes 0, here, some magnetization remains in the material. This remaining value is known as retentivity or remaining from here to, right? If we go on decreasing, when negative direction if we apply H value, the magnetization becomes 0 at a point. The required reversal field is called coercivity or coercive field. From here to here, this field what we call coercive field or coercive force. Upon further reversal, replication of the magnetic field, the material once again reaches the saturation, tracing a complete loop from A, B, C, D, E, F, again A. This is a complete loop. So the closed path traced by magnetization is called hysteresis loop, showing the lag of magnetization behind the applied magnetic field. And this concept can be explained based on a orientation of the domains as well. So at a saturation, domains are oriented in a one direction completely, and in a opposite direction the domain orientation will be completely opposite, but in the middle the domain orientation slowly changes. So in this way we can explain this hysteresis curve, right? Thank you. Hi engineers, in this lecture we are going to discuss about soft and hard magnetic materials. So depending on the size of hysteresis, BH curves or IH curve, ferromagnetic materials are classified into two types mainly, soft and hard magnetic materials. So if the area of the hysteresis loop is very small, that is what we call soft magnetic material. And whenever this area of the magnetic field is very high, then we will say it is hard magnetic material, right? So what is remanent pole, remanent field and coercive field, all those things we studied in hysteresis curve. Just refer that video if you require more information on the part how these loops are formed. Here we classify the materials based on hysteresis loop area as a hard magnetic materials and soft order magnetic materials. So when come to the properties and applications, these materials, hard magnetic materials, demagnetization are known as it is very hard to demagnetize. Losses are very high. Hard magnetic material, high coercivity, low initial permeability, high hysteresis energy loss, high remnant polarization. So this is the high coercive field, high remnant field, and high saturation flux density, low susceptibility, low eddy current loss. All these are the properties of this hard magnetic material. Examples of alloys of aluminum, nickel, cobalt, copper, and iron, tungsten steel alloy, chromium steel alloy, etc. Where we will use these hard magnetic materials? Basically in small motors, in hand tool, Walkman equipment, CD motors, MRI, magnetic resonance imaging, body scanners, computer applications. Those places we will use this hard magnetic material. The next one is soft magnetic material, ferromagnetic materials, in which are easily magnetized and demagnetized. So when come to the hard magnetic materials, it is difficult to magnetize as well as demagnetize. But when come to soft magnetic materials, it is very easy to magnetize as well as demagnetize. It has low coercivity, low hysteresis loss, high permeability, then high susceptibility, low remnant magnetization. When come to the examples, alloys of iron, nickel, silicon, commercial iron, alloys of nickel, copper, chromium, iron, all these materials has this soft magnetic nature, where we can use core of the transformers, power generators, audio frequency applications, right? Like this, in different applications we use this soft magnetic material. When come to the differences in the exam, sometimes they will ask compare between soft and hard magnetic material. Whenever we are writing these parameters, always include the diagram. That is a good idea. Soft magnetic materials can be easily magnetized, demagnetized, it is a hard. Then small magnetic field magnetizes a soft magnetic material. Since domain walls move easily and reverse, it is hard to magnetize. It consists of very steep hysteresis loop, broad hysteresis. Its hysteresis area is small, loss is low, but this area is high, so loss will be very high. They have large value of susceptibility and permeability. When come to this one, it's a low value. The coercive and retentivity values are small. For this hard magnet, it is a large. When soft magnetic materials are used in preparation of magnetic core materials used in transformer, electric motor, magnetic amplifier, this is used in loudspeakers, microphones, magnetic detectors, etc. Thank you for watching this video. Hi engineers, in this lecture we are going to see about the application of magnetic materials. So magnetic materials ni ekkadekkada vaadtamu anedi ఈ వీడియోలో చూడబోతాం. జనరల్ గా మ్యాగ్నెటిక్ మెటీరియల్స్ అనేవి ఎలక్ట్రోమాగ్నెటిక్ మెటీరియల్స్ ఉంటాయి, అంటే ఆర్టిఫిషియల్, న్యాచురల్ మ్యాగ్నెట్స్. సో ఇక్కడ ఆ డిఫరెన్స్ ఏమీ లేదు, బట్ వీ యూజ్ మ్యాగ్నెట్ ఎక్కడైనా వాడినా సరే అవన్నీ ఇక్కడ కవర్ చేద్దాం. ఎలక్ట్రిక్ మోటార్స్ అండ్ జనరేటర్స్. సో used in rotating machines to convert electrical energy to mechanical energy and vice versa. మోటార్స్ లోను జనరేటర్స్ లోను వాడతాం. మోటార్ ఏం చేస్తుంది అంటే ఎలక్ట్రికల్ ఎనర్జీని మెకానికల్ ఎనర్జీగా కన్వర్ట్ చేస్తుంది. జనరేటర్ ఏం చేస్తుంది అంటే మెకానికల్ ఎనర్జీని ఎలక్ట్రికల్ ఎనర్జీగా కన్వర్ట్ చేస్తుంది. ఈ రెండిట్లో కూడా we use magnet. Transformers and inductors. Soft magnetic materials are used in core to improve the magnetic flux and efficiency. Transformers లోను ఇండక్టర్స్ లోను ఈ సాఫ్ట్ మ్యాగ్నెటిక్ మెటీరియల్స్ వాడతాం. Magnetic storage devices. Hard magnetic materials are used in hard disks, magnetic tapes, and credit debit cards. Then electromagnets used in cranes to lift heavy metal objects in scrap yards and industries. దీనికి జనరల్ గా సాఫ్ట్ మ్యాగ్నెటిక్ మెటీరియల్స్ అనేవి వాడతాం, ఎందుకంటే ఈజీలీ వీ కెన్ మ్యాగ్నటైజ్ అండ్ ఈజీలీ డిమాగ్నటైజ్. MRI, magnetic resonance imaging. Strong magnets are used in medical imaging to scan internal ఆర్గాన్. ఇక్కడ కూడా ఎలక్ట్రోమాగ్నెటిక్ కాకపోతే హై టెస్లా ఉన్నాయి వాడతాం, హై ఇంటెన్స్. స్పీకర్స్ అండ్ మైక్రోఫోన్. మ్యాగ్నెట్స్ కన్వర్ట్ ఎలక్ట్రికల్ సిగ్నల్ ఇంటూ సౌండ్ అండ్ వైస్ వర్సా. స్పీకర్ ఏం చేస్తుందంటే ఎలక్ట్రికల్ సిగ్నల్ ని సౌండ్ సిగ్నల్ గా మారుస్తుంది. మైక్రోఫోన్ ఏం చేస్తుంది అంటే సౌండ్ సిగ్నల్ ని ఎలక్ట్రికల్ సిగ్నల్ గా మారుస్తుంది. మ్యాగ్నెటిక్ లెవిటేషన్, మ్యాగ్లెవ్ ట్రైన్స్, సూపర్ కండక్టింగ్ మ్యాగ్నెట్స్ హెల్ప్ ట్రైన్ ఫ్లోట్ అబౌవ్ ద ట్రాక్ రెడ్యూసింగ్ ఫ్రిక్షన్. సో ఈ సూపర్ కండక్టింగ్ బేస్డ్ ట్రైన్స్ లో వాటిని డెవలప్ చేయడంలో కూడా మనం ఈ మ్యాగ్నెటిక్ మెటీరియల్స్ వాడతాం. కంపాసెస్ అండ్ నావిగేషన్ టూ. సో పర్మనెంట్ magnets help in indicate Earth's magnetic north and south. Then electric bells and buzzers, so work in electromagnets to produce sound. Magnetic locks and security system, use doors, safes and electronic security device. Then sensors and switches, so magnetic sensor, hall based sensor, ఇవన్నీ కూడా మనం డిఫరెంట్ వాటిల్లో వాడతాం. రీడ్ స్విచెస్, డేటా స్టోరేజ్ ఇన్ కంప్యూటర్. మ్యాగ్నెటిక్ మెటీరియల్స్ ఆర్ యూజ్డ్ ఇన్ ర్యామ్, cache memory and magnetic sensors. Magnetic separation in industries, use it to separate magnetic materials from mixtures. మైనింగ్, రీసైకిల్స్ ప్రాసెస్ లో ఈ మ్యాగ్నెట్స్ అనేవి వాడతారు. టెలికమ్యూనికేషన్ డివైజెస్, మ్యాగ్నెటిక్ కోర్స్ ఆర్ యూజ్డ్ ఇన్ యాంటీనాస్, సిగ్నల్ ప్రాసెసింగ్ అండ్ కమ్యూనికేషన్. సో ఇలా మనం మ్యాగ్నెటిక్ మెటీరియల్స్ ని డిఫరెంట్ వాటిల్లో యూజ్ చేయొచ్చు. ఓకే, థ్యాంక్ యూ ఫర్ లిజనింగ్ దిస్ వీడియో.